In this section, we'll take a look at an example using the data set called CARS. You can find this data set if you go to the lab data sets, and it's called CARS, the CARS data. Let me pull that in here. So in this data set, we have some characteristics about different types of automobiles. We have the miles per gallon for each automobile. We have the number of cylinders, the size of the engine, the horsepower of the engine, the overall weight of the engine, acceleration, model year, and then we have this origin variable. The origin variable takes the characteristic of a 1, 2, or 3. It's a 1 if its country of origin is American, 2 if it's European, and 3 if it's Japanese. Now, we have a problem because this origin variable is categorical. So we can't use the origin variable by itself. What we're going to do is create a a dichotomous variable from this categorical variable. So we'll actually create 3 dichotomous variables. We'll create a USA, a European, and a Japanese. To create this dichotomous variable, we're going to use a logical statement that says if the origin variable equals 1, give me a 1, else give me a 0. So for all the American-made automobiles, we'll have a 1 in this column. For all the non-American, we'll have 0. And we can copy those down by double-clicking. And you can see down here below that when we get to non-American, we get zeros. The same for European, so we're going to use an if origin equals, in this case, 2, give me a 1, else give me a 0. Copy that down. And then Japanese. So if origin equals 3, give me a 1, else give me a 0. Copy that down. Now we want all of our independent variables together, so we want to get this categorical variable out. So I can't just copy, I'm going to cut this, and then that will put this over here, and that still keeps the reference as it was before. But now we have these 3 dichotomous variables. These are what are called indicator variables. Sometimes they're called dummy variables. But we can't, the purpose here is we can't use this origin variable because it's categorical. Let's look at some descriptive statistics that we have on these variables. So the average, median, standard deviation, minimum, maximum, and count is all reported. This is what is called descriptive statistics. It's a good kind of first step to give your reader or somebody that's reviewing your work an idea of your data set without actually showing them the data, the entire data set. They can get kind of an idea for the ranges. Then we took a look at a t-test comparing the American vehicles to the non-American vehicles based on miles per gallon. We find that non-American vehicles, on average, have a higher miles per gallon rating than an American vehicle. And we find that this value is statistically significant. It's close, but it's statistically significant. Oh, excuse me, it's not close. Okay, not close. T-stat is negative 13.48. the absolute value of that is much greater than 1.97. And so we can say that the American vehicles have a statistically significant lower average miles per gallon than non-American vehicles. Well, there's a problem here because we know that typically American vehicles are larger, they have more horsepower, they have more cylinders, and so that's naturally going to cause higher miles per gallon, not just the fact that they are simply have a lower miles per gallon rating. We want to be able to control that. So let's take a look at first that correlation matrix. So we go to data analysis, and we can show how these different variables are interrelated. We can actually see this multicollinearity. To capture the entire data set, I do have labels, and this is a big matrix, so I'm going to allow this to go into a new sheet. So if this is our dependent variable, we can see that there's a high degree of correlation between each of these variables and miles per gallon. But what a correlation matrix doesn't tell us is how these independent variables here are interrelated. Just for example, let's just look at the number of cylinders. More cylinders means you've got a bigger engine. It means you have more horsepower. It means that you're going to have more weight. The acceleration goes down, but that's actually a good thing. Okay, model year, the type, we can see here that the United States vehicles, American-made vehicles, have more cylinders. They're positively correlated with cylinders, whereas European and Japanese automobiles are negatively correlated with number of cylinders. That's going to affect horsepower. And we can see similar correlations as we go down through each of these independent variables and compare them to one another. So we have a high degree of multicollinearity. We need to address that, but our goal here is really just to predict the miles per gallon and then talk about or take a look at this relationship of American vehicles versus non-American vehicles. So I'm really more concerned with whether it's an American vehicle or non-American vehicle, so I'm going to be most interested in this USA variable. I'm not going to include so much the European and Japanese variables. So this variable, this dichotomous or indicator variable, is going to tell me the relationship after controlling for all of these other factors. So I go to my regression in data analysis. My miles per gallon is my dependent variable. That's what I'm comparing here. I want to control for cylinders, engine, horsepower, weight, acceleration, model year, and then compare American vehicles to non-American vehicles. I do have labels. I'm going to allow this to go onto a new worksheet. Expand that. So let's take a look at what we found. We can describe a significant portion of the variation in miles per gallon. 82% of the variation in miles per gallon is described by our combined variables. Our model has a very low significance F, much less than alpha, so we can say that the model as a whole is predictive. It has statistically significant predictive power. Now let's look at each one of the individual variables or coefficients. We don't really need to look at the intercept because the intercept only means something if all of the other variables are zero. We obviously can't have an engine that has 0 cylinders and 0 size and 0 horsepower. So the intercept really doesn't mean anything in this case. We can look at the significance level of the other variables. So let's highlight those variables that are significant. Cylinders is not significant. The t-stat's less than 2, the p-value is greater than alpha. Engine is significant. Horsepower, not significant. Weight is significant. Acceleration is not significant. Model year is significant. And after controlling for these other variables, we also find that the USA value is significant. Now we have a lot of multicollinearity. I think we have engine is highly collinear with cylinders. Horsepower is probably highly collinear with weight. And acceleration is probably the same way. We don't want to exclude those variables just because they have a low t-stat, but we need to recognize that there is a lot of multicollinearity. Ultimately, if we just assume that all of these are multicollinear, then we want to compare just the USA variables to the non-USA variables, and we find that on average, when we go from a 0 to a 1, indicating an American made, the differences in miles per gallon is now 2.7 miles per gallon. This really isn't significant. Now there's an argument to be made here that the model year should not be included because the model year may have some, maybe pulling some of that descriptive ability away from these other variables because maybe automobiles are getting smaller, maybe automobiles are getting smaller, getting larger. So as one final check, let's run this regression absent of, I need to get back into my data set, absent of our year variable. So in Excel, if I want to exclude a variable, I can't just pick around it. I've got to physically cut it out, and I don't want to lose it, so I'm going to insert it on the right-hand side. We could look at maybe taking some of these other variables out, comparing the r-squared, seeing if it drops, but we'll leave it in. We'll run the regression. Our dependent variable remains unchanged. Our independent variable will now include all of the same variables except for the year. And we'll allow that to go onto another sheet. Just as we suspected, the comparison between USA and non-USA variables was stronger because we had the year variable. We shouldn't have had the year variable. We find that the difference is about 2 miles per gallon after accounting for the size of the engine, the horsepower, the weight, these other characteristics that are collinear with American vehicles. But we still find that they are, on average, about 2 miles per gallon lower in miles per gallon or fuel efficiency than non-American made vehicles.